In the previous module, we have learned about different operations like shift, scale, and flip, both along the dependent variable and along the independent variable. If we make the changes to the independent variable, we play with the variable inside the parenthesis, that is the argument. If we play with the dependent variable, we make the changes to the amplitude. For example, if you want to shift the signal upwards or downwards, that means we are playing with the dependent variable. We represent that as x of t plus or minus c. On the other hand, if we play with the independent variable, say for example we want to shift the signal leftwards or rightwards, we represent that as x of t plus or minus c inside the parenthesis. So if we want to play with the independent variable, make the changes inside the parenthesis. If you want to make the change to the dependent variable, make the changes outside the parenthesis or to the amplitude. Similarly, the scaling operation. If we write c into x of t, we are scaling along the dependent variable or the vertical axis. Depending on the value of c, it gets amplified or attenuated. But if we write x of ct, where ct being represented inside the parenthesis, the signal gets shrinked or stretched along the horizontal axis or the independent variable. Similarly, the flipping operation, when we write minus of x of t, the signal gets flipped upside down. That means it gets flipped along the vertical axis, that is the dependent variable. So the signal that is there on the top goes towards bottom, and the signal that is there at the bottom goes up. On the other hand, when we represent a signal as x of minus t, that means we have changed the independent variable, the variable inside the parenthesis, the signal gets flipped along the horizontal axis or the independent variable. So the part of the signal that is on the left goes towards right, whereas the signal on the right goes towards the left. It's simply acting as a mirroring operation. Now that we have learned about these operations, shifting, scaling, and flipping individually, we may look into a combination of these operations. The combination could be either we may perform these operations like shifting, scaling, flipping one after the other. So depending on the sequence of these operations, the end result changes. The operations along the dependent variable are easy to understand usually, whereas the operations along the independent variable is somewhat tricky. Let's look at the combination of these operations specifically for the case of independent variable. Let's make combinations of, say, shifting and scaling first. So consider these cases. Case 1. Say for example, the signal x of t let's try to shift this signal, say by a factor of b. So the resultant signal will be x of, well, we are making the shift in the independent variable. So we need to make the changes inside the parenthesis. So the resultant signal would be x of t minus b. Assuming that we are shifting this signal towards right by a factor of b, let me write that. So this is shifting by a factor of b. Now let's try to scale the resultant signal. Now please note that we are scaling this signal along the independent variable. What is the independent variable here? T. B here is simply a constant which is being obtained by shifting the original signal. So it is some value, it's a constant. Whereas the variable here is T. So we must now tune or change this T. Say for example, now we are scaling the resultant signal by a factor of A. Therefore, the resultant signal will be x of AT minus B. You may note the changes here. We are only scaling the independent variable just because we need to perform the operations along the independent variable. So here we have performed scaling by a factor of A. Now let's take another case. Let's exchange the order of these operations. Case 2. Consider the same signal x of t, but now instead of shifting the signal, we scale the signal. As we are scaling the signal along the independent variable, so we need to change the parameter inside the parenthesis. So the resultant signal, the expression would be x of AT. What we have done here, scaling by a factor of A. Next, let's now shift the signal. Let's do the shifting operation first. We are doing the shifting operation followed by the signal that is being obtained after scaling. So we are now performing the shifting operation. So the resultant signal will be x of A. Well, you should note here that the shift is being done to the independent variable, that is t here. We should not touch A because A is simply a constant. Therefore, the resultant signal would be A of t minus B. So what we have done here, we have simply done the shifting operation, shifting by a factor of A. Sorry, the factor is B here. Now observe these two cases. In the first case, we have performed the shifting operation first and the scaling next. In the case 2, we have performed the scaling first and shifting next. Well, you can clearly see that these two resultant signals are different. They are not the same. Therefore, the shifting and the scaling operations cannot be interchanged for the same value of A and B. Let me write that. Shifting and scaling operations cannot be interchanged. for same values of A and B. Let's take an example. Let's take the same example that we have seen in the previous module. Let x of t be something like this. It starts from 0, 1, 2 here. The amplitude is 1 and this is the t-axis. Let this be x of t. Let's take the first case. In the first case, as we have seen here, we're doing the shifting operation first, followed by a scaling. So let's shift this signal by some amount. Let that amount be, say, 3. So the resultant signal will be x of t minus 3. Let's try to plot this signal. So it is the same signal being shifted rightwards by 3 units. So the resultant signal will be like this. So 3 would come somewhere here. And the remaining remains the same. 1 here, it will be 3, 4 and 5, and this would be the amplitude 1, this being t. What is this? The shifted signal. So let me try it, shifting first. And then we are scaling the resultant signal. So say for example, we are scaling the resultant signal by a factor of 2. So the resultant signal would be x of 2t minus 3. You may see that the changes are being made inside the argument. Therefore, when we try to scale the resultant signal, we have seen that in the previous module, the x-axis or the horizontal axis simply gets divided by that scaling factor. So the 3 here will get mapped to 1.5, the 4 here will get mapped to 2, 5 here will get mapped to 2.5 and so on. Why? Because the scaling is being done to the independent variable by a factor of 2. So the resultant signal will look something like this. So this 3 will come to 1.5. It will be somewhere here. It will go to 2 and go down to 2.5. So here it will be 1.5. This will be 3 and here it will be 2. This axis again being t. So what is this signal? The signal is being obtained by scaling The second step is scaling. So these were the operations that we have performed in case 1. So let me write that. These were the operations that we have performed in case 1. You may see here in case 1 we have shifted the signal. There's a mistake there. It's shifting. We have first shifted the signal followed by a scaling. So we have shifted the signal followed by a scaling. So we got this resultant signal whose amplitude is again 1. Let's take the second case. The original signal is now being scaled first. So let me draw the scaled version of the signal. So as we have seen that the resultant signal would be x of, now scaling has been done with the factor of say 2 again, so it will be x of 2t. The original signal being represented as x of 2t will look something like this. As we have seen that in scaling, as we are scaling by a factor of 2, simply the x-axis or the horizontal axis will get scaled or will get divided by a factor of 2. That's it. So the resultant signal will look something like this. 0 being intact, 1 will be at 0.5 and 2 will go to 1. And so on. So this here, it is 0 followed by 0.5 and 1 here. The axis is t. What is the signal? This is x of 2t. What we have done here? We have simply done the scaling first. And now we will try to shift this signal. So the signal now would look something like this. Now we are trying to shift this signal, say by a factor of 3 again. So the expression would be x of 2 t minus 3. So the signal would be something like this. So the signal is shifted by a factor of 3. So this will start all the way around at 3. That is from here. I'll mark the axis. So it will start from 3, it will go to 3.5 and 4 here. So what we have done here? We have done the shifting. Now let's observe these two cases. Now the case that we have seen recently is case 2. So the operations that we are performing on the left is the case 1, where we have first shifted the signal followed by a scaling. Whereas the case 2 on the right, we have scaled the signal followed by shifting. We may easily see by observing these two graphs on the left and the right that these two operations are clearly different. The resultant signals are different. This demonstrates that the shifting and scaling operations cannot be interchanged for same values of shift and scale. We shall look more into this in the next module. Thank you.